Now we're going to talk about the kind of problem that we want to be solving in Unit 4. So just like in Unit 3, how we talked about solving systems of equations, in Unit 4 we're going to be working on solving linear programming problems. And linear programming is a type of problem where you're trying to optimize a specific quantity given a bunch of constraints that you need to simultaneously satisfy. So we'll have maybe some sort of profit function that we want to be optimizing. So we want to figure out the biggest profit that we can make given a bunch of constraints, like maybe I can only manufacture so many units, or I only have so many labor hours that I can put into this, or I have a certain budget constraint. So all of those constraints will be represented by inequalities like this, and if we put all of the constraints together, then we'll get this system of inequalities, and that will tell us the region over which we are trying to optimize. And the thing that we're optimizing will be represented by some separate function, like a profit function or whatever. So throughout these kinds of problems, we're always trying to find a maximum or a minimum value for some given quantity. And here's how we solve those problems graphically. So just like in Unit 3, we will first talk about how to sort of solve the problems in an elementary way, and then we'll develop a method for solving the problems by using matrix manipulations. So the matrix manipulations part will come next time, but for now we're just going to talk about how to solve these kinds of optimization problems graphically. So here are the steps. We're going to first graph all of the boundary lines, and then we'll choose some test point that doesn't live on any of the boundary lines and star that point in the graph. And then we'll test that point in each inequality in that problem, and we will shade the true sides of each line. And then we'll identify the region for which all of the inequalities are true. So these first 4 steps are basically the same thing that we did up here. The point that we used as our test point was the origin, and then we just shaded the side of each of our boundary lines that belonged in the feasible region, and then once we knew the intersection of all of those solution sets, we could darkly shade the feasible region. So this feasible region is what we call the intersection of all of these. So the region where all of the inequalities are true is called the feasible region. That's supposed to say shade it darkly, sorry. Shade is darkly. This is the region of all of the solutions to the system, so it'll be the simultaneous solution set for all of the inequalities. And now steps 5 through 7 are the new things. So here we're labeling all of the corner points for the feasible region, and then we'll write down all of the corner points, and then the corner points are going to be the points that we plug in to the function that we're trying to optimize. So the way that these problems will look is like this. They'll always look like maximize some objection function subject to a list of constraints. Those constraints are going to be inequalities like the ones that we had above. And what we'll end up getting is a feasible region like this. So this would be the region that would be darkly shaded like we saw above. And now notice that this region has a bunch of corner points. So those are points that do not belong to, or sorry, maybe I should say points that belong to more than one boundary line. So these regions will have a bunch of corners. You can make a list of all of the corner points. And what's interesting is that for the kinds of functions that we're going to look at, which are called affine functions, the objective best value for that, I should just say the best value for the objective function is given by evaluation at one of these corner points. So we know that the maximum for whatever we're trying to maximize is going to happen at one of these corner points. We just have to test all of these corner points to see which one of them gives us the maximum. And then we found the maximal value for our function on this region. Now, the thing that I just said is technically only true whenever you have a bounded region like this, so some region that has finite area. In the solution set that we saw up here, this region would have infinite area, And what happens in this context is that either the optimal value for your objective function happens at one of the corners, or it does not exist. So it's possible to have some objective functions that do not have a global maximum, but instead they just sort of continue to increase as you go up and right, for example. But if the optimum exists, it will be guaranteed to happen at one of these corner points. So we're going to sketch the region, and then we're going to look for the corner points, and then we will identify the optimal solution by just plugging in each of the corner points into the function that we're trying to optimize. So here's an example where they've already sketched the feasible region for us. So the feasible region looks like this. And it says we want to find the maximum and minimum values of this objective function. So the objective function is usually called z. That's what we're trying to find the biggest or smallest values for, and z is given by this expression, 2x plus 4y. So we want to find the biggest value for 2x plus 4y on this shaded region, and we also want to find the smallest value for 2x plus 4y on the shaded region. And what's interesting is that the maximum and minimum are guaranteed to occur at one of these corners. So we only have to test these corner points. So I'll list the corners. The corners are 1, 1, 4, 8, 7, 7, and 9, 2. You could just read those off from the graph, but they've been nice to us and just told us what those corner points are. And now we will test our objective function at each of those points to see which one of them gives us the max and which one gives us the min. So if I plug in 1, 1, that would mean that our x value is 1 and our y value is 1. So our z value would be 2x plus 4y equals 2 plus 4, since both x and y are 1, which would be a 6. Similarly, this second corner would give us a 2 times 4 plus 4 times 8, which would be 40. And then if I plug in 7, 7, then that would give us a 2 times 7 plus a 4 times 7, which would be a 42. And then lastly, if we plug in 9, 2, then our x value would become a 9, and our y value would become a 2, and we would get an 18 plus an 8, which is a 26. And now we wanted to find the maximum and minimum values of the objective function. It looks to me like the minimum value is a 6. So this is our minimum z. And the maximum z that occurs on this region is 42. So what that means is that if you plugged in any of these points, so if you were allowed to plug in any points that live in this region, if you wanted to minimize the value of z, then you would plug in this corner, 1, 1. And if you wanted to maximize the value of z on this region, you would plug in this corner, 7, 7. So we've now found our maximum and minimum z. So now we've seen all of the steps that are involved in solving a linear programming problem. Now I'm actually going to show you a linear program. So this is what a linear program looks like. It's basically just a combination of the stuff that we've seen so far. So a linear program is always going to say maximize or minimize this z value, subject to some list of constraints. And what we're going to do is we'll follow the procedure that we talked about above. Namely, we'll start by graphing the feasible region. So I'm going to take that list of constraints and I'm going to treat it as a system of linear inequalities. We'll graph the feasible region, we'll identify the corners of that region, and then we'll plug in those corners to see which one maximizes the thing that we want. So let's start by just graphing this feasible region. So notice that all of these are non-strict inequalities, so the boundary lines belong in the solution set. And notice that again, these last inequalities just say that x and y need to both be positive. That again just means that we have to live in this first quadrant. So we're happy with anything that lives in the first quadrant over here. So you can basically ignore that bottom constraint for now and focus just on the x plus y needs to be less than or equal to 8 and the 2x plus 3y needs to be bigger than or equal to 6 constraints. So for the first one, let's graph the boundary line. So that's the line x plus y is equal to 8. If you set y equal to 0, then x would have to be 8. So that would be this point that belongs on the line. If you set x equal to 0, then y would have to be 8. So that would be this point up here. And that gives us this diagonal boundary line. Similarly, if we have equality for the second constraint, then we would have 2x plus 3y equals 6. If y is equal to 0, then x would have to be 3. So that gives us one point that lives on that second boundary line. And then similarly, if x is 0, then y would have to be 2 in order to get equality there. So that gives us that point that lives on the boundary line. And now we will connect those to determine our boundary line like that. And if you'd like, you can also go ahead and plot the boundary lines that are represented by the axes. So this would be the boundary line that says that x needs to be bigger than or equal to 0, and this would be the boundary line for saying that y needs to be bigger than or equal to 0. So here are all of our boundary lines. And now we need to determine which region here is actually the feasible region. So I think the test point that I'm going to use is actually just for these first two lines, I'll use the origin again. You could use any point here, but usually it's easiest to test the origin. So we'll see whether the origin belongs to the solution set for that first inequality. So if we're looking at the x plus y needs to be smaller than or equal to 8, I would plug in 0, 0, because that's our test point, and that does satisfy the inequality. So that means that this side, so the lower side of that first line, is part of our feasible region. And then if we try something similar for the second inequality, I'll plug in 0, 0 there. Then I would say that 0 plus 0 is supposed to be bigger than or equal to 6. That's false. So the origin does not belong in the solution set corresponding to this second boundary line, and that means that the solution set for the second boundary line lives above the second boundary line. So our solution set should live here. It should also live to the right of this vertical line, and it should live above this horizontal line. So that tells us that the feasible region is this region here. It's also sort of a good hint that this is the only region that's bounded by all four of the constraints. So if the feasible region were any other region, then one of these constraints would be ignored by the feasible region. So that gives us a good hint that we've gotten the right answer here. But we're not done, because what we need to do is we need to find all of the corners now and then test which corner is actually going to give us the optimal value. In this case, we only want to maximize z, not minimize it. So we just need to find which one of these points maximizes z. So I will make a list of the corners, and then we'll also make a list of the objective function values at each of the corners. So it looks to me like the corners are going to be 0, 8, 8, 0. Whoops, there should be a 3, 0, and a 0, 2. So there should be 4 corners here. There's our list of corners. And now I'm going to plug into the objective function. So if I plug in 0, 8 into the objective function, then I would get that z is equal to 0 plus 8 times 8 plus 37. And if you'd like, you can simplify that, but we actually don't really need to. We just want to know which one of them is the maximum first. So I'm not going to worry about simplifying till the end. If you plug in an 8 for x and a 0 for y, then this would be a 6 times 8 plus 0 plus 37. So for all of these, I'm just plugging into the objective function definition up here at the top. Similarly, if I plug in a 3, 0, this would be a 6 times 3 plus 0 plus 37. And for the last one, I would get a 0 plus 8 times 2 plus 37. Now, we're just looking for which one of these values is maximal. Notice that all of these have a plus 37. So that's not going to advantage any one of these terms. We can basically ignore that term. And then we just need to decide which of these expressions is largest. And the largest of those would be the 8 times 8. So that will give us the maximal value up here. And that means that the max z value occurs at 0, 8. And that max z would be a 37 plus an 8 times 8. So if you compute that, then what you end up getting is what? 8 times 8 plus 37, 101. So our max z value would end up being 101. So usually in these linear programming problems, we'll be reporting both of these bits of information. So we want to know what the parameters need to be in order to maximize z, but we also care about what the maximal z value is. So we'll see some examples next week of what these different variables could mean, but this might be, x might be the number of hours that you need to bring in a certain person, and then y might be a number of hours that you'd need to bring in a certain other person in order to maximize z, the total number of documents that they can type up, something like that, right? So we'll have some reasonable constraints that we set on our situation, and then this would say that you can type up 101 documents if you don't bring in the first person and you bring in the second person for 8 hours, right? If this were some sort of word problem. And all of the constraints would come from some sort of word problem constraints, like the total number of hours that they can work is at most 8. That would be, for example, this top inequality. Oops. Sorry, I can't seem to write. There we go. So this is just saying that the total of x and y has to be smaller than or equal to 8. Maybe that would correspond to saying something like we can't afford to pay for more than 8 labor hours, for example. But we'll focus more on the interpretations of these problems later. For now, I just want us to sort of get used to the mechanics and the idea of trying to optimize something over some finite region. So in the next video, we'll finish this out by looking at this problem